Hi and welcome to this chemistry lesson. We are starting a new topic today and we are referring to chemical energy changes and specifically looking at enthalpy today. So if you have no idea what I'm talking about, stick around and you'll definitely learn something. Okay. Let me start by explaining a very simple concept that is not very difficult to understand, and that is when what happens when we have a molecule. Okay, so if I have a molecule here, I'm going to look at hydrogen peroxide. Okay, so hydrogen peroxide is a molecule with two oxygens and two hydrogens. Okay, hydrogens are actually here. One hydrogen there and one hydrogen there. So it's almost like water. Okay, and you can get water in some reactions from it, but hydrogen peroxide is O2, H2O2. Okay, H2O2. Now, in order for this molecule to stay together, there are forces at work that's keeping it together, that's attracting these molecules together, and that forces involve the sharing of electrons, or in ionic bonds, for example, it involves the attraction that two different charges of ions have. Okay, but nevertheless, there exists a force keeping these atoms together. Now, if there's a force that keeps them together, in order to break that force, or in order to break the bond, we will need energy to break that bond. When we break that bond, energy is released. Okay, now that means that this molecule contains energy. There's energy contained in this molecule, so that if I can break the bond, energy would be released. If something contains energy that would be released given a certain event to happen, that energy is called potential energy, and we use U to show its potential energy. Okay, if we do this, if we break up this molecule into its substituents, or not substituents, into its the elements that make it up, we get the one has oxygen. We'll get oxygen, and we will get hydrogen. Okay. Now, these two molecules in themselves also has potential energy. Okay, so if I were to take this one will have potential energy, and this one will also have potential energy. Okay, now this is a reaction. It's a two-way reaction. It can go both ways. Okay, but the point being is that we have potential energy in my original molecule, and then potential energy in these two molecules as well. Now, if I take the total potential energy on this side, okay, and the total potential energies on this side, it does not necessarily mean that the total potential energy on the left is equal to the potential energy on the right, because the amount of energy needed here and the amount of energy needed here together might be more than the energy needed in the beginning, or the energy we had in the beginning might be more than the energy we have now in the new molecules. Okay, so if I were to take the difference between the potential energy of the products minus the potential energy of the reactants, reactants. Okay, this is not necessarily equal to 0. Okay, in other words, they're not necessarily the same, so that it adds up to 0. Okay, but what it does give me is the enthalpy. Enthalpy. This is what enthalpy is. Okay, and you'll understand in just a minute why we call this the heat of the reaction. Heat of the reaction. Okay, so in other words, enthalpy is the heat of a reaction. And in short, we will use delta H as the symbol for enthalpy. So delta H is the symbol of enthalpy. So H is actually defined, let me show you, H is actually defined as the potential energies, the internal energies keeping molecules together, plus the this is pressure times volume. Now if I do this H, okay, which is called enthalpy itself, but this would be the enthalpy of a specific molecule. So the enthalpy of a specific molecule is the internal forces plus the product of the pressure and the volume. But now if I do this for the products, so I have one for the products and I have enthalpy for the reactants, okay, which is the internal forces of, or the internal energies of the reactants plus the pressure in the system and the volume of the system. These two are the same, so that if I subtract these two, in other words, I take the internal energies of, or I take the enthalpy of the products minus the enthalpy of the reactants, this part of, assuming of course that we keep pressure and volume the same, then that part will cancel out because I'm subtracting, they will cancel from each other. So in the end, enthalpy, or the change in enthalpy technically is, this is the change in enthalpy, but change in enthalpy is called the heat of a reaction, and that's the difference between the internal forces, in other words the potential energy of the product, and the potential energy of the reactants. Okay, not internal forces, sorry, I keep using the wrong word, internal energies. Okay, now if we consider this, consider now the internal energies of the products is bigger than the internal energies of the reactant. So again, we're talking about the total internal energies and the total internal energies. Okay, now if that is true, that the products have more energy in themselves, okay, than the reactants had, it means that we needed some energy in order for this system to have occurred. In order to go from here to there, we need energy, we need extra energy so that we can actually have the bonds to form. That means that in order for my energy before and my energy after to be the same, if I wanted the total energy in the system, not just the total internal energies, the total energy okay, before to be equal to after. Okay, I've got my energy, the internal energies of the reactants, and afterwards I've got the internal energies of the products, but this is more than that, so it means I need to add some energy. And how do I add energy? I add it in the form of heat. Okay, now imagine that I have the total internal energies of my products are less than the total internal energies of my reactants. That means if I take the internal energy of the reactants and the internal energy of the products, this time my products have less energy in the molecules itself. That would mean that I used to have more energy, and after the reaction happened, what happened to the extra energy? Well, it was released in the form of heat. Okay, it can be heat or light. We'll stick to understanding it as heat. Okay, but it will be released in the form of heat. So the point is that heat can be a reactant. Look here, heat forms part of the reactants. Can be a reactant or a product. Okay, and here comes the important conclusion. Okay, if I were to have that the internal energies of my products are greater than the internal energies of my reactants, notice then the difference, the enthalpy of this reaction will be positive. Okay, so enthalpy will be positive. It will be greater than 0. If my enthalpy is positive, again, you don't have to go and learn this off by heart. You just need to know that enthalpy is the change of internal energy in the products minus the reactants. So if it's positive, it means I've got more internal energies in the products than I had in the reactants. Okay, which means that my products have more energy than my reactants. So in order to form the product, I needed energy in my reactants, which means that this is called an endothermic reaction. Now, endothermic means heat had to be added, energy had to be added to the system. The opposite would be exothermic. Thermic, you can hear that word is heat. Thermic is heat, like a thermometer measures the heat in the atmosphere. Okay, so if I have my internal potential energies are less than the internal potential energies of the reactants, the internal energies of the products less than the internal energy of the reactants, then it means that after the reaction occurred, okay, I've got excess heat. I've got excess energy that is released in the form of heat. Okay, because otherwise what happens to that energy? And this will happen when my enthalpy is negative. Okay, so negative enthalpy means heat is released because negative enthalpy means I've actually have an excess of energy. Positive enthalpy means that I need energy. So you can almost look at enthalpy as the amount of energy needed. If the answer is positive, I need energy. If the amount is negative, I am giving away energy. Okay, I hope that makes sense. I think the last thing I can just mention about enthalpy is the unit that we use. Okay, so the unit that is used for enthalpy for, let me use this one as an example. The enthalpy for this reaction is about 187 kilojoules, that's a capital, kilojoules per mole. Okay, which means that for every mole of hydrogen peroxide that is broken up into oxygen and hydrogen, okay, 187 for every mole, 187 kilojoules is, okay, now notice that it's a positive, and this is the enthalpy. Okay, so this is positive, which means we need energy. Okay, so I would have to add heat in order to break the bonds in here and then produce new bonds in there. Heat is needed for this reaction. Okay, and 187 kilojoules of energy is needed for every mole of hydrogen peroxide that is broken up into oxygen and hydrogen. So I hope that makes sense. You can go and look at any compound that you can imagine and go and Google the compound, and if you go to Wikipedia, that's for example where I got this value. If you go to Wikipedia, it will give you in a column on the side the enthalpy of that reaction. So let me actually show you. Here we have the Wikipedia article on hydrogen peroxide. Okay, here it shows you what the molecule looks like, and it gives you a bunch of information here on the side. And you'll notice if I go down here, the formation, the standard enthalpy of formation, okay, is negative 187.8 kg. Now you might ask, but no, wait, you just said it was positive. Okay, this is enthalpy for formation. That is how much energy is needed to form. For the reverse reaction, that is the amount of energy it needs to form this one. So obviously, to go in the opposite direction, okay, it would be the negative amount of this. So in other words, if I had hydrogen peroxide, okay, on the one side as a product, so hydrogen peroxide as a product and hydrogen and oxygen as the reactants, then this would be the standard enthalpy. Okay, but if I go in the opposite direction and look at the decomposition of hydrogen peroxide, it would be the opposite sign of this one. So that's just to explain where I got the 187 from. And sorry, I should have rounded better. It's 188 actually if I round it. But nevertheless, you can look at any compound you can imagine. Let's look at sodium chloride. Okay, there we go, sodium chloride. And if we look at sodium chloride, which is standard, there we go, the standard enthalpy of formation. So to form sodium chloride between sodium and chlorine, it will have an enthalpy of negative 411 kilojoules per mole. Now again, to form, so sodium plus chlorine will have an enthalpy of negative 411. So in other words, if I have sodium chloride as a product, okay, then I'll, under standard conditions, that that is defined elsewhere, and we can look at that later, but under standard conditions we'll have a enthalpy or change in enthalpy of negative 411. Negative means I've got less energy in my products than I had in my reactants, which means energy was released. So this standard formation will be a exothermic reaction. Heat will be released. Well, that's all I want to say on this topic. I hope you enjoyed it and you learned something. See you in the next lecture.